Okay, and welcome to Chapter 2, Mapping GIS Data. So this chapter starts to introduce you into the concepts of what it takes to not only place data onto a map, but start to differentiate it from itself, so to speak. So, and telling the story via colors and symbols and making and different decisions that you have to make as a map maker and understanding what kind of data there is. And we'll get more into that as we go along here. So first of all, when you first add data to a map, it just kind of comes up as a single color, whether it be points, lines, or polygons. It's up to you to create a scheme that makes sense to the person using the map. And you could do that in several ways, depending obviously on the geometry. So if you have points, you have some options. You have lines, you have some options. And you have polygons, you have options. And if you have font, you have options. And a lot of times you have to, make decisions as to what you're trying to get across. So for example, with points, you can see that we can vary by shape here. So we could use different shapes for different entities, whatever those may be. We can show a different size, let's say with population. That kind of makes sense. The smaller the dot, the smaller the population, the larger the dot, the larger the population. We could do the same thing with thickness of lines. So the thinner the line, the less traveled that particular road, or maybe the thicker the line, the more traveled. Or you could use sort of standardized lines. So these dashed lines here at the bottom kind of always represent unpaved rural dirt type roads. Maybe it's sort of a normal road, a highway, and then an expressway. So you get the idea with line thickness. You don't have a lot of options when it comes to lines other than color and thickness. So another option is obviously for polygons, you have color and patterns. Now, color is used a ton in GIS, obviously, because we're looking at this on color computer screens. So color makes a huge difference. And you want to be able to differentiate the different polygons from each other. However, if you're doing certain things and you want to, let's say, print in black and white, then patterns might be another option. And obviously you might recognize some of these from geology, like a limestone or a sandstone, a shale type situation. So it depends on what you're trying to do. Or you could use a combination of the two. You could use a limestone with let's say a colored background. And finally, font. Now all maps should have some kind of labels on it because we're visual beings. We want to be told where things are. So just like a website, right? You have a title on a website, and then you might have a subtitle, normal looking text, maybe something that's bold or emphasized or italicized. All of those things play a role visually as to how you're trying to tell the story. And the same thing applies in a map. So let's say you want to, emphasize the city names. So maybe you make them a bit bigger, a bit bolder. Rivers are typically italicized and maybe a blue color. They look like they might flow along the river. Text, font, and style of, or size, color, and style of their fonts, excuse me, are vitally important just as much as the symbology. Because again, labels, everything has a name to it, whether it be a street or a building or whatever. You have to make choices and pick and choose what's important, what isn't important. You don't want things overlapping and creating sort of a jumbled mess. And then on top of that, you could differentiate, like I said, with size, color, and style. So all of these things for points, lines, polygons, and fonts, you have to make a decision. So you do that, and it takes a little bit of practice, but as you do it more and more and more, the decisions become much easier, and you'll start to understand there's sort of a pattern to your patterns, so to speak. So real briefly, I'm going to touch on these. A lot of people haven't done a lot of, let's say, website design or maybe photo imagery enhancements or whatever. You have to understand how color works, okay? And I'm just going to go over this briefly. In a nutshell, let's be honest here. A lot of it has to do with just sort of your favorite colors. When you're making a map, you're going to use a color scheme that best represents what the phenomena is you're mapping, but also there's some biases involved in that with other things. Maybe you don't like the color orange and you'd rather use a light green to dark green color or something like that. So all I'm going to say with this is that this is the hue saturation value color model. And they have a percentage of hue saturation and value. That's what these HSV stand for here. But again, it's unless if you're using an exact color, you can kind of, move the sliders around to where you want. The other color model, which is a bit more well known, is the RGB or red, green, blue color model. This is used quite a bit, for example, in website design. I've been using this for years. Just to kind, it's pretty easy. You have 0 is black, 255 is white or bright, and then all the colors therein are in between. So 000 is absent of color or black. 255, 255, 255 is all of the colors mixed. It's an additive model. So when you add them all together, you get white. And then the gray shades are when you have all three of the numbers the same except somewhere in between. So let's say 10, 10, 10 or 30, 30, 30. Those are gray shades. And then you have something like the yellow, which is 255, 255, and 0. So there's no blue whatsoever. Okay. So it's an additive model. And again, you don't have to memorize these by any means, but understanding how the color models work will make it much easier to get to a color you're trying to get at quickly. And there's nothing wrong with using customized colors. There's no law saying you have to use red, green, yellow, blue. It's very okay to use custom colors and things if it suits what it's trying to portray, or if you just want to make it look nice, right? You get to kind of put on your artistic hat for a little bit, as long as it fits what's going on. So we can use color in various ways, and color, being that we're humans and visual beings, color is very important on a map, especially a map, because you're trying to tell a story and you get sort of one shot to do that. You use different colors in different ways. So here's three options here. You can use color by category, and we'll talk more about categorical data in a minute. Okay, so every type of road gets a different color, or every type of volcano gets a different color. So they're sort of unique colors in a way based on what phenomena you're trying to map. So maybe blue is water, green is forest, yellow is um, agricultural, orange is, you know, uh, something else. I can't think of what, and pink is urban. So that might be one option. Then you have the quantity variance, which is here in the middle, and that's what we call a monochromatic scale. So it starts with a light color and goes down into a dark color. And what that does is show change, just like the thickness of the line that I mentioned in the previous slide. The lighter the color, the less of the quantity. The darker the color, the more of that quantity. And if let's say we use, for example, population, a light color would have less population, the darkest color would have the largest population. It's pretty self-explanatory. I'm sure you've seen this on maps many times. Another option is what's called the divergence scale, and these are used for very specific reasons. Typically, those are used with things like statistical packaging, looking at standard deviations or hot spots and cold spots. So the blue would be a cold spot, the dark orange or usually a red would be a hot spot. Things like that. They have very specific uses. They're not usually used for the middle column, the quantities one or the categorical one. Those are used much more often, but the divergent ones are very handy for certain types of data sets. Not warm, cold values. It could be, temperature, right? That's a good one. So blue is cold and orange is warm. Things like that. So it's used for very specific purposes. So when you're making maps, you're not just putting data on a map to show people. You're trying to tell a story. And different maps are used to display different types of data. So you have to understand the different kinds of data there is. And I don't mean points, lines, and polygons like I mentioned back in chapter 1. This is more along the lines of, okay, I have points, lines, and polygons. How do I best symbolize them according to their data types to tell that story? What's the best way to do that? And because most of our data, not all of our data, but a lot of our data is numeric, but not all of it. So there's different kinds of maps for different kinds of data. So the first one you can see here is single symbol map, and that's basically just making a pretty map. And it's what we use. It's uses nominal data. Now, nominal, we'll talk about all these different data types in a second, but nominal data is, it's just basically place names. You place all this stuff on the map. There's no change in colors or nothing like that. It's just strictly showing you what's there. And that's okay. Sometimes that's all you need. You also have unique value maps, which are maps used for categorical and ordinal data. Again, I will discuss these as we go further, but those are two more types of data. So you have nominal data, categorical data, and ordinal data. Those are three different data types. For numeric data, there's a couple of different options. There's graduated color types, which I kind of showed you before with the light to dark color scheme. You have graduated symbol maps, which is like a small dot to a large dot to show population differences in cities, small dot, small population. You get the idea. You have dot density maps, which are, let's say, population density. You're going to have more dots in an area with more people in a smaller area. And you have chart maps, which aren't used very often, but they are doable in GIS and can be quite helpful. So I'm going to show you some examples of all these and explain what all this means. So nominal data is unique names or uniquely identifies objects that might be on a map. County names, airport names, tax ID numbers, parcel ID numbers. If you don't know what a parcel is, the city keeps track of their tax base by the footprints of buildings. So every building has a footprint and they call that a parcel. So my house, your house, UWM, Lapham Hall, they all have a footprint that sits on the ground and that has a unique number. Just like we have a social security number, although you don't want to use those, we have a social security number. These have unique identifiers. Each feature is likely to have its own value. There's only one um, tax ID number for each building or whatever. Typically within at least a state, there's only one county with the one. You're not going to have two Jefferson or two Milwaukee counties in Wisconsin. That doesn't mean there might not be another Jefferson County somewhere else in the country, but within the state itself, there's only one. So what nominal data is typically used for is labeling. All right. When you want to show the labels for the cities or airports or roads or rivers, you get that from nominal data. It's a column in the attribute that has all of those unique identifiers in there. These also come in handy sometimes for what's called joining tables, which we'll get to later in the semester. So these unique identifiers are very, very helpful for a lot of things. And it makes doing GIS and combining data sets and things like that possible. The next type of data is called categorical data. So this is the type of data that on its surface looks like just one kind of data, for example, volcanoes. But we all know, being geoscientists, I hope, that there are more than one kind of volcano. And within the attribute, there's probably a column that differentiates the different types of volcanoes. Well, what would be nice is rather than have all the volcanoes with the same exact symbol, I'd like to show each different kind of volcano with a different symbol. That means the volcanoes are separated by category, and this is categorical data. So as you can see here, the volcanoes have different types to them. Now this word type is not just there, that's an actual column in the attribute table called type that says whether or not it's a stratovolcano, a caldera, a complex volcano shield, or volcanic field. You get the idea. So there's different categories of each type of volcano. The same thing applies, now that's for points, so the same thing applies for lines. You have highways, and within the attribute table there's a column called class. And in that class, differentiates the different type of highways. Is it an interstate? Is it a freeway? Is it an arterial or unclassified? Okay. And you can, once you tell the program to use this type of symbolization scheme, it makes your map much more robust in terms of not just having one line for every single road, but different symbols for each type, or in this case, class of road, to help so the reader could say, oh, that's an interstate. Oh, that's a freeway. The last one is using example is for, let's say, land cover type. So, or geology is another one. Okay. So you have different kinds of land cover, and in the, like I mentioned before, in the attribute table, there's a column called cover type, and in there is the different types of cover, and you can show that on a map. Okay, or let's say, like I said, geology, kind of like this map up here in the upper right, right. That's probably geology. So it gives you an impression of what's going on geologically because each geologic formation has its own color. The next type of data is something called ordinal data. It's a type of categorical data, but it's based on rank. And those ranks are arbitrary. And you'll see in this example. So the snail habitat rank is 0, which is unsuitable, 1, which is marginal, 2, acceptable, and 3, ideal. Now, there's no differentiation between a 0 and a 1, or a 1 and a 2, or a 2 and a 3. You don't really see what that criteria is. You only know that a 3 is better than a 2, that is better than the 1, that is better than a 0. Okay, so it's a ranking. Your grades are ranks A, B, C, D, and F, right? You know, there's no, it's kind of an arbitrary scale. I could just say, all right, I'll give you L, M, N's, O's, and P's. It's just how the grading scale was set up. You see this quite often in certain things, and sometimes this data is really handy for generalizing things, especially for the public, the general public. They don't need to know the particulars of the difference between a 1 and a 2. What they all want, what they care about is just seeing sort of where the optimal number threes are. Let's say that's where we want to go snail hunting over the weekend with my family. They want to know where those threes are. That's where they're going to try to get to. Now this uses what's called a unique values map, and this is an option in GIS when you add data and you go to your symbolization scheme. It'll say unique values. Okay, and then you have your option for what you want to use. A lot of times you want to use a hue-based color scheme. So the monochromatic scale I mentioned where it goes from light to dark. So again, ordinal can be very handy with certain data sets. So the bulk majority of the data that you're going to use in GIS is numeric data of some sort, whether it's something that you download or something that you generate yourself based on calculations. By far, most of the data you're going to deal with is numeric in value. So there's two main kinds of numeric scales. There's the interval data that you see here on this slide. An interval places data values along a regular numeric scale. So for example, elevation is a good one. It supports only addition and subtraction. You can't multiply or divide interval data and get meaningful results. However, it can have negative values, which means there's no meaningful 0 point. So you can think of elevation, you can go below sea level, right? Temperature, we go below 0 here in Wisconsin, unfortunately. So temperature and elevation are both examples of interval data. In fact, that's how I remember it. All right, you'll probably be quizzed on all this stuff. You have to know these different types of data. So interval data can have negative values and go below 0, like elevation and temperature. So the next data type is called ratio data. And ratio data places values along a regular scale with a meaningful 0 point. What this means is it cannot be negative. So for example, population, you can't have negative population. It supports addition, subtraction, multiplication, and division. Obviously, you can't divide by 0, but you get the idea. So again, it's a meaningful 0 point. You cannot have negative values, Anything that involves, like, for example, precipitation. You can't have negative precipitation. So that precipitation and population are both ratio data types. Now, the more you do GIS, the less you actually have to think about this. It'll just make sense to you. Hey, I need to use this type of scaling system for this. And while it is very handy to know the difference between interval and ratio, their color schemes are identical. You can use the same color schemes pretty much within reason for both. So we call that mapping quantities data. So both interval and ratio data must be divided into classes. I also sometimes you'll hear me use the word bins. It's an old term that I learned way back a long time ago. So classes and bins are the same thing. It's the starting and ending points of where one symbol starts and then the next symbol starts. So for example, in the cities down here in the bottom, the first class is 8,200 to 300,000, and then 310,000 to 1.6 million. You get the idea. So those are the classes, the starting and ending points. Now these happen to have 3 for both the points and the lines in between, in the middle here, excuse me. And then you have 4 classes for the precipitation. You have complete control over the number of classes that you use. Now, typically there's some rules on how many classes you should make. Maximum would be 5, maybe 6 or 7, depending on what you're trying to do. And obviously you don't want to keep it too small because then you're not showing any variation whatsoever. So usually it's between 3 and 7 classes. There are some exceptions to that. Um, the thing is especially when you're doing um, let's say like this type of thing where you have differences in colors, the human eye can only see so many different color tints. So the more, if you're adding 9 classes, it's really hard to see the differences sometimes between the colors. So you got to keep that within reason. And changing the number of classes is a drop-down menu. It's super easy. There's no guesswork involved in it whatsoever. You can play around. If you don't like 4, you can try 5. If you don't like 5, you can try 3. You can play around with it. It's just a drop-down menu. You can change it to whatever you need it to. Now, when you're placing these types of data on maps and changing color schemes and everything to, you're creating what are called classed maps that places features into ranges and vary color or symbol size. So that's called a classed map. So for example, you have population or population density or the state capital's population varying by the size of the dot with that population in it. That's called a classed map. That's not a term I use very. It's sort of a generalized, okay, it's a class map. I don't think I've never not made a class map because you're almost always going to use graduated color or graduated symbols on a map to show differentiation between the different phenomena taking place. You'll see this term once in a while, choropleth. All that means is a change in color scheme. So we're using different colors to measure the absence or presence of a quantity. And to do that, we use color, hence the term choropleth. That's all that means. So you can really screw up a map if you use the wrong color scheme for your map. So if you look at example A here, um, you can see that there's definitely a differentiation between the light and dark colors. Okay, there's some phenomenon that is more here than down here. And I'm going to assume this is just, for example, this is population. This is Oregon. So this county down here and that one has much less population than, let's say, this one up here, because that's where Portland is, the largest city in Oregon. Now, if I change the color scheme to what's called a divergent color scheme, which is a cold to hot, this map down here in B makes no sense whatsoever. There's no way to understand why this county is red and this one down here is blue. Now, you really, really have to think about it. So using a divergent scheme like this doesn't make sense for population density. However, it would make sense for something like hot and cold spots, let's say looking at crime rates or something like that, but that's a statistical measurement. You can also have unclassed maps, which are proportional symbol maps or dot density maps that avoid potentially artificial or subjective data groupings. So these are just generated automatically. So let's say we're looking at the population of the state capitals. These dot sizes and the 10,000, 100,000, 1 million, those are automatically generated. You can't mess with them. That's just how they're going to come out. So it's kind of like a de facto standard. This is what you're going to get. The same thing with the dot density. Those dots are placed randomly. They're there to show population density. There's no cities actually where those dots are. It's just showing that, hey, there's more people in this area per area or more less people per density. So when you're mapping with class data, one of the things you have to keep in mind is what's called the modified areal unit problem, or MAUP. What this is you have a summation plus the problem of area. Okay, so if I showed you a map in map A here, this is the total number of farms, the sum of the number of farms in the United States. Well, you can see that Texas is by far has the most number of farms. Why is that? Well, it's the largest state, so it has the most room to put the most farms. Well, one of the things with that is it doesn't really show us anything. It's like, okay, yeah, that's totally gonna the expected result. So what can happen is that maps have a tendency to reflect the influence rather than the data being mapped, and that's based on area. So rather than map sums, you should almost always map percentages by area. So, sort of like a density, farm density, population density, it gives a better representation of not just the number of farms, but the number of farms crammed into the area that's being mapped, and gives a better representation of, okay, here's what's actually going on, not just, oh, hey, this is a huge state, we got a lot of farms. So the way to minimize having the MAUP, or the modified areal unit problem, is by normalizing or dividing the data by a suitable field that allows the data patterns to emerge. So if you use the number of farms as an example, you have the number of farms and then you have the number of farms per square mile. So here's the number of farms over here. So we expect that, right? That's Texas. Texas has the most space. It's going to get the most number of farms. Then over here, if we divide that by area, now we get a much different picture. That's telling us, hey, there's lots of farms crunched into the area of these particular states, including Wisconsin, as you can see. This tells a much better story as to what's really going on in the state. Not just, hey, we have a lot of farms, but hey, we have a lot of farms despite the fact that we're a much smaller area. The same thing can be applied to the number of vacancies for homes. So if you look at this map here in the lower left, map B here, you would completely expect that that California, Texas, New York, and Florida would lead the list of the number of vacancies. Why? Those are the four most populous states in this country. Okay. So yeah, they're going to have the highest number of vacancies just because they have more people. So again, you divide that by the number of housing units available, and it tells a much different story. Now all of a sudden you can see that states like Arizona and New Mexico and Montana and Wyoming, along with some of the other states, like even Florida still have a high rate of vacancies for the area that is given. So dividing each value by the total of all the values is another way to normalize the data. So divide the number of congressional districts in each state by the total number of districts to view the percentage of Congress controlled by each state. Well, this should still be fairly easy to interpret because the number of congressional districts is dictated by the population. California by far and away has the highest population in the country. So it's gonna have the highest percentage of Congress controlled by the state, and then followed by Texas, Florida, and New York. Okay, because again, that's where the population centers are. But if we didn't divide that out, it would be dictated by just the area again. So there's different ways that you can show what's truly happening within a given area, and you should almost never just map sums. You should almost always be mapping percentages to give the better picture. So here's large polygons tend to dominate the map. We saw that with Texas with the number of farms. They are prominent and attract more attention even when the values are low. So when we took area out of the question, Texas wasn't even one of the darkest ones, like in A here. So this is the farm, going back to the farm thing. Now you can see there's sort of a region in the upper Midwest here, upper Ohio Valley, Mississippi Valley, um, that has the highest number of volume, or excuse me, farms per area. Whereas before, Texas and California just dominated the whole map. Well, they're huge states and they do have a lot of farms, but it's not telling the whole story. So the mountain states stand out in the farm density for a lack of farms. You can see that all the way down here. That kind of makes sense if you understand the geography of the United States. There's a lot of desert there, mountains, things like that, high elevations that aren't very conducive to farms. And then Maine has a high vacancy rate but commands little notice in a national map. So this means, Maine is in there. However, you might have to adjust these values a little bit to kind of show off the fact that Maine might lead the list. And those are decisions that you have to make as you make the map. So reducing visual MAUP, you can use densities. Instead of using polygons is what they're trying to get at. Instead of using polygons with color like here, you can use the dots with various sizes because the dots are sort of neutral. There's no color. You could kind of still get the same trend that, hey, there's more farms in this area of the country up in this area here than let's say out west per area without having that dark color scheme dominate what you're looking at visually. And the same thing applies with the number of farms and um, just placing random dots. So a dot density does the same thing. It sort of makes the fact that it's arbitrary. There's no bias being inherently put into the map because of color schemes, and us as human beings, we visually see darker colors and they stand out to us. These two maps on the right sort of alleviate that issue. Okay, so switching gears a little bit, we're going to talk about raster types a little bit. Now again, rasters are near and dear to my heart. It's what I do for the most part. Um, Being that we're in the geosciences, we have a tendency to map natural phenomenon, which are done much better through rasters. That's not to say you don't use vectors, and the program ArcGIS makes it really easy to convert between rasters and vectors going in either direction. However, you do need to understand that there are two very different kinds of rasters. There's what's called the discrete raster and the continuous raster. Now, the continuous raster we talked about a little bit earlier, where each cell has its own value and it might vary slightly to create a continuous surface like elevation or precipitation. Okay, so there might be thousands or even millions of potential values in these in the cells for a given elevation surface. Very few cells have the same exact number. Whereas in the sort of the opposite of that is the discrete raster, where you have objects such as roads or land use polygons. Land use is sort of the common one I use as an example. You have large areas with the same value. So using land use as an example, looking at this middle diagram, you can imagine that the blue color here is water, the green color is forest, the pink color is sort of urban, industrialized, and then this beige color over here is agricultural. So when you're out in the real world, you have large areas of urban, you have large areas of water, you have large areas of forest and large areas of farmland. They don't have just they don't vary from cell to cell. You have large numbers of cells with the same exact value. So that's what makes discrete data, discrete rasters a little bit very different than continuous rasters. They don't have very many values, and the cell values don't change out necessarily right away. So just like with vector data, you can create thematic rasters, color schemes and things like that. Contain quantities that represent map data such as geology or elevation, may be continuous or discrete. So if you look at example A, that's a geologic raster. So you can see the various different colors. However, the colors are, for lack of a better term, blobby because geology doesn't always change with every single cell. There's large areas because of formations. So A is a discrete raster. B is a raster that's it's an elevation raster, but it looks kind of weird compared to C, where C looks really smooth. B is an example of a classified raster, which is also considered a discrete raster. It kind of takes all the values and lumps them together into classes. And then the final one over here on the right in image C is what's called a stretched raster, which gives the appearance that of smoothness and a nice continuous surface. So when you display these types, just like you do with vector data, you have to understand what kind of data you're dealing with. So categorical or ordinal rasters have a tendency to use unique values or discrete colors, similar to what we saw in vector world. Okay, so A and B would use discrete colors, whereas an interval can use either classified or stretched methods. Excuse me, A is the only one that's discrete. I apologize. A is discrete. B and C are both um, uh, quantities rasters. However, you can use B and C. B is a classified raster, like I mentioned in the previous slide, and C is a stretched raster, which gives it that appearance of smoothness. By default, when you bring in a raster, it's typically stretched, unless if it's a discrete raster. The program is very smart in understanding what kind of data is being brought in, and usually, not always, will pick the scheme you need for it. Now, when I say stretched, what do I mean? The program is reallocating the raster values to fit within the black to white color scheme, the 0 to 255. All right. What this does is it improves both brightness and contrast. And there's different kinds of stretch types, such as min, max, or standard deviation. Now, 99% of the time, you don't have to worry about this. You really don't. However, there are some formats out there, namely the USGS formats, where sometimes you'll have to change the stretch type manually. Otherwise, you get this thing in the middle, this B. You can barely see that. Okay, so when you bring in a USGS DEM, oftentimes you get what looks like a big black box. And that's only because the stretch type wasn't defined. Then using a drop-down menu, you change the stretch type to min-max, which is right here, and lo and behold, boom, you'll get C. So sometimes there's just an added little click here or there to get the data to where you need it to be. So stretching is just a visualization technique that the program uses so we can see it sort of in all of its glory. Image rasters, which is something we don't use a ton of, are just that. They're satellite imagery. So taking a picture of the surface of the Earth somewhere, okay? And those are also stretched typically, But they also have, there's usually either single band or multi-band rasters. Now, single band rasters are just stretched sort of like black and white, whereas the RGB composite ones have 3 bands and allows you to do some pretty cool remote sensing stuff where you can mix and match the bands to get various different visualization techniques to look at things like that. How healthy is the vegetation, what urban sprawl, ice, things like that. And then you have what's called an indexed color raster, which is basically a scanned image. So you can think of this as the old USGS topo maps, and they have specific colors that are built in, so to speak. I don't use these because they're just not very pretty, um, but they're still there and you can still use them. Okay, so when you're mapping with numeric data, you at some point have to make decisions on how you're going to class your data. And there's lots of, you can see there's 6 different classification schemes, and I'm not going to go over all of those. The book does explain them a little bit better. Over the years of teaching this class, what I found is that for almost all data sets, the default classification method works the best for almost every data set you can imagine. Okay, so what is this doing is it's dividing data into class ranges, each with its own symbol. So you have, and you tell it how many ranges you want. So in this case, all of these examples have 5. It applies to both vector and raster maps. There's different classification methods. Like I mentioned, there's 6 of them sitting here. And the choice affects the map appearance and the validity of the data. You can get very, very, very different maps depending on which classification scheme you use. Now, what you can do is you can use some of these different classification schemes to see, kind of bring out what's going on in the data, or what they call exploratory methods. However, let me explain though that of all these classification schemes, this first one here, box A, Jenks Natural Breaks, is the default and by far the most used classification scheme. And for 99% of what you're going to do in GIS, it's perfectly good. And I'll go over that in a second. But that is the default one, and very, very rarely have I ever changed it other than for a very specific reason. So the Jenks Natural Breaks classification, again, is the default one for the program. It exploits natural gaps in the data, and it's good for unevenly distributed or skewed data. Okay, so if you don't know what that means, you have the classic bell curve of data, okay, where you have essentially the mean and median are right down the middle. Very few data sets follow that exactly. You usually have some, it's either skewed off to the left, it's skewed off to the right. You might have 2 highs or 2 lows, and data can be very weird that way. So the Jenks takes advantage of the fact that most data is unevenly distributed and works with it the best. It's the default and it almost never needs to be changed. You might play around with them somewhat in the tutorials, but trust me, after all the years I've been doing GIS, I almost never have to change that method. But here's the other ones. So the defined interval or equal interval classification, it puts everything into equal size classes. You can change the ranges for it, and the user chooses the number of classes for each. You could think of this as sort of the manual method, and sometimes that does help. Especially, you'll notice if you look at the numbers in here, these are really nice round numbers. You got 84 to 1000, 1010 to 2000. So somebody had to manually go in there and do that. And I strongly suggest it's okay to do that. Okay, that's defined interval. It's sort of a manual method. Okay, and then you have equal interval, which is putting the same number of everything in each class. Again, these are splitting hairs, and typically you don't have to mess with it too much. Then you have the statistical classifications, which are probably a little beyond what we do in this class. It puts the quantile puts the same number of features in each class. The standard deviation classification compares values to close to and far from the mean. That one of all of them besides the Jenks, the standard deviation one is kind of nice because it really gives you an understanding as to where the outliers are, so to speak. Okay, so if you look at this particular map, everything in yellow is perfectly within the confines, so to speak. Okay, nothing much going on there, but the blue and then sort of the brownish color, those are areas that are telling you, hey, there's something going on above and beyond where it should be. These are abnormally high or abnormally low values, and you could do some more exploring to figure out what those might be. So, for example, looking at these abnormally high values, high standard deviations in the mountain states here, that might be worth looking into using other statistical methods. You have the geometric interval classification, which multiplies each class by a constant. It's best for visualizing strongly skewed or logarithmically increasing data such as population density. So this might be another option for that you could use, but again, it's not something you're going to do very often. It has very specific uses for it. So if you have data sitting out on a hard drive or a cloud server somewhere, and you add that data to your map, it becomes a layer. Now layers within the map store, display, and label properties. And you can have multiple people accessing one piece of data all at the same time and making maps that look vastly different, as you can see in this particular slide. So that's sort of the beauty of GIS. And it's something I want you to remember that I mentioned in the previous chapter slides is when you remove a layer from your map, you're not deleting the data, you're just removing the link to the data from your map. Now, when you remove data from your map, you are in a way deleting the symbology and the label properties that go with it, unless if you create what's called a layer file, which then you can reuse those properties over and over and over again. So layer files are just that. They're a file, once you have all of your symbology and all your fonts and labels and everything that look just perfect and pretty and where you want them, you can save those as what's called a layer file. Now, it's a way to be able to transfer the same symbology to multiple maps or projects. Think of it kind of like a symbology template. However, if you have a layer file, you have to transfer it with the same exact data that it was created with in order for it to work, which is one of the reasons I'm not a big fan of using them. It can be kind of weird to do that. They can be used to enforce special or consistent symbols on many data sets. Okay, and that's again a templating thing, especially when you're working in a, let's say a company environment where they want everything to be consistent across the board. This is a great way to be able to do that. Styles are a set of symbols stored together. It may have a specific theme or use, and they're viewed and selected via the symbology pane. So within ArcGIS, there are a ton of styles. Tons. There's the ESRI styles, which are sort of the default ones. You have all of the USGS 1 to 24,000 map styles. So any symbol that you might find on a USGS 1 to 24,000 map, you can use those symbols in ArcGIS. You have all kinds of little 3D cool little building ones. You have utility symbols, geologic symbols, all kinds of symbols that you have at your fingertips to help symbolize and tell the story a little bit better. All right, so that's the end of chapter 2 now. Hopefully you're starting to get an idea that, the data itself is what's important. And how you symbolize it and tell the story um, is going to play a huge role as to whether or not your map is, effective in trying to get your point across. So in the next chapter, which is presenting data, we're going to go even further into some of the decision making that's going to take place when making an actual map. So stay tuned and I'll see you in chapter 3.